In today's video lecture, we will go through reaction intermediates. Before this video lecture, we were doing homolytic and heterolytic bond fission. So knowledge of homolytic and heterolytic bond fission would be used here, right, in reaction intermediates. In case you have any doubts on homolytic and heterolytic bond fission, I would suggest you to go through my previous video lecture, right. So reaction intermediates, right, we'll go through reaction intermediates now. As the name says, intermediate. Intermediate is something that comes in between, right? So here, since we are studying about mechanism of organic reactions, we have reactants, and then on the other hand, on the other side, we have products, right? So between these reactants and products, we have reaction intermediates, right? And these reaction intermediates help in the progress of reaction towards product side, right? How? Because these reaction intermediates that gets formed, right, during the course of reaction are highly reactive, short-lived species, right? They are high reactivity, helps promoting the reaction towards in the forward direction, right, towards the side of reactants, right? So reaction intermediates basically are, these are formed during the course of reaction, right. Since these are intermediates, so just to understand, these comes between reactants and products, right. Now your homolytic bond fission and heterolytic bond fission will lead to the formation of reaction intermediates, right, like we did before in previous video lecture. We saw that when a bond, right, because we know that when a chemical reaction takes place, any chemical reaction involves breaking and making of bond, right. So when a bond breaks, right, it will form reaction intermediates, right, and based on how bond is broken, right, whether the bond is broken homolytically or heterolytically, you have different reaction intermediates, right. If the bond breaks homolytically, then what gets formed is your free radicals, right, which are neutral reaction intermediates. And if the bond breaks heterolytically, and the bond breaks heterolytically due to the presence of electronegativity difference between the combining atoms, right, or between the bonds, or the bond that is getting formed, right, between the atoms, those atoms have electronegativity difference, right. So when the bond breaks, the atom or the group which has higher electronegativity will take away the electron pair, right, acquiring a negative charge, right, and the other that has lower electronegativity, which may be a heteroatom or the carbon atom of the organic molecule, it will acquire a positive charge, right. So if the heteroatom has higher electronegativity, the carbon of the organic compound will get a positive charge, and if the electronegativity of the heteroatom is less, then carbon will acquire a negative charge, right. So based on the positive and negative charge, the positively charged carbon atom is your carbocation, right, and your negatively charged carbon atom is your carboanion, right. Now in this video lecture, we will look into the structure of these reaction intermediates and their reactivity, right, their reactivity order, right, and their stability. So you have bond fission, right. Bond fission is of two types: homolytic bond fission and the other is your heterolytic, right. In homolytic bond fission is like this. It's when each of the atom, when a bond breaks, each of the combining atoms will take one electron each, right? Because a bond is made up of 2 electrons. So when this bond will break, A and B will take 1 electron from the bond, right? So here A will have 1 electron and B will also have 1 electron, right? And these are neutral species, right? And we call these as, these are free radicals, right, and are neutral, right? And these are highly reactive and short-lived, right? What is the reason for their high reactivity? These free radicals have odd electrons, right, or they have single electrons, right? And every species, right, that have a single electron will always try to pair up the odd electron or the single electron, right? So in an attempt to acquire one more electron, right, it will immediately react with the other reagent, right? So because of its single electron, its reactivity is high, right? Because in order to pair up, it will immediately react. This is highly reactive, and it's highly reactive due to odd electron, right, which it will try to pair up, right? Now let's talk about heterolytic bond fission. Heterolytic bond fission is like this, right? When you have electronegativity difference between the combining atoms, right? So one which has high electronegativity will take away the electron pair that is forming this bond, right? This bond is made up of 2 electrons. So both the electrons will go with the atom that has high electronegativity. In this case, let's say B has high electronegativity. So A will acquire positive charge and B will acquire negative charge, right? And remember, B has both the electrons of this bond, right? So this species, right, is your anion, right? In organic chemistry, we will call it as carboanion, and this is positively charged, so we call it as carbocation, right? Now carbocation is short of electrons and carbanion has excess of electrons, right? So it has a pair of electrons. So this is highly reactive because it can donate its electron pair to the other species and react. This is highly reactive because it can accept electrons, right? Because it is short of electrons, so it can accept electrons. So due to electron deficiency and electron excess, both carbocations and carboanions are highly reactive, and these are also short-lived reaction intermediates, right? So these have excess electron pair, right, and this is short of electrons, right? Now since we are talking about chemical reactions, right, so before product will get formed, right, the substrate, right, or the organic compound that is undergoing a chemical reaction will form these reaction intermediates, either free radicals or a carbocation and a carboanion, right? And since these are highly reactive, short-lived, so these reaction intermediates will further react to form products, right? So in a way, these reaction intermediates will help in the progress of reaction, right? So just one more thing, we know that in a chemical reaction, in any chemical reaction, what we have is, so let's just write it over. We have a reagent and a substrate, right? Now these reaction intermediates, right, is formed from this substrate, right. Now these substrate, right, these intermediates, these reaction intermediates is formed from this substrate, and this substrate is an organic molecule, right, and this is a reagent which is reactive, it is highly reactive. So mostly you will see that when a reaction is taking place, the substrate, that is an organic compound, will break homolytically or heterolytically to form the reaction intermediates, and this reaction intermediate would immediately be attacked by this reagent, right, to form products, right, because this substrate initially is less reactive, right. So when a reaction is taking place, your substrate, the organic molecule, is less reactive, right, which is changed into highly reactive reaction intermediates, right. So when it is changed into highly reactive reaction intermediates, it would be attacked by the reagent. This is how a chemical reaction takes place, and this reagent can be positive or negative, right. Now in this case, the intermediate can also be negative, positive, or neutral, right. Neutral is your free radicals, and positive and negative are your carbocation and carboanion, right. Now suppose a positive ion is formed, say this, or a negative ion is formed, right, or the other, you have an odd electron neutral species. This is an odd electron free radical. So this positive would immediately be attacked by the negative reagent, and if you have a carbanion, which is a negative reaction intermediate, it would immediately be attacked by the positive reagent, right, because these are also short-lived, right. We'll just look into its orbital picture also. And this free radical, we know that free radical has an odd electron, right. So this odd electron, in order to pair up, right, will immediately react. So this is how normally a chemical reaction occurs, right. Now let's quickly look into the free radicals. Free radicals is formed as a result of your homolytic bond fission, right. Now before we go through these reaction intermediates, there is one little thing, types of carbon. There are 3 types of carbon, right, depending on its connectivity to other carbon atoms. It can be primary, secondary, or tertiary, right. We also call these as 1 degree, 2 degree, or 3 degree. If carbon is connected to one carbon atom or no carbon atom, right, this is your primary, right, or 1 degree carbon atom, right. Now if the carbon atom is connected to, say, 2 other carbon atoms, this is your secondary carbon or your 2 degree carbon. If carbon atom is connected to 3 other carbon atoms, this is your tertiary carbon or your 3 degree carbon, right. So depending on primary, secondary, or tertiary carbon, your free radicals are also primary, secondary, or tertiary, right, depending on the carbon atom, right, that has an unpaired electron or that has a single electron is primary carbon atom, secondary carbon atom, or tertiary carbon atom. Depending on that, the free radical is also primary, secondary, or your tertiary, right. For example, if we talk about primary carbon atom, this is you have 1 electron here, so this is your primary free radical, right? Or if it is like this, because this methyl group has a carbon atom. So in a way, this carbon is connected to one carbon atom, right? If it is connected to all the hydrogen atoms, no carbon atom, then also it's a primary free radical. Primary radical or your 1 degree radical. Notice that odd electron in case of free radicals. Now if you have two alkyl groups is like this, it's like this, right? So you have one, let's write it like, let me write it like this in order to avoid the confusion, right? So here this carbon atom that has an odd electron, right, since it is an odd electron, it has resulted from a homolytic bond fission, right? And this carbon atom that has an odd electron, right, or it has a unpaired electron, it is connected to two other carbon atoms, right? So this is your secondary carbon atom, secondary free radical, or your 2 degree radical. Similarly, if it is combined to, if your carbon atom is connected to 3 other carbon atoms, this is your tertiary, right, or your 3 degree free radical, right? So depending on the carbon atom, whether it is primary, secondary or tertiary, your free radical is also primary, secondary or tertiary. Remember, these free radicals always contain an unpaired electron pair, right? I hope this is clear. So now just let's quickly look into its orbital structure. Free radicals are planar mostly, right? They are planar. The carbon atom in free radicals is sp2 hybridized, right? So if this is the carbon atom, we know that carbon is tetravalent, right? It is tetravalent and it is sp2 hybridized. That means one s and 2 p orbitals hybridized to form 3 orbitals, right? And 1 p orbital is unhybridized, right? So this 1, 2 and your 3, these are sp2 hybrid, or these are 3 sp2 hybrid orbitals which will overlap with s orbitals, or these s orbitals of hydrogen atom, or they will overlap with methyl radicals, right? They also have 1 electron, right? So this is a sigma bond. This is when these overlap, they will form sigma bonds, right? You should know chemical bonding for this. And 1 orbital, 1p orbital is unhybridized, right? Like this. This is your unhybridized p orbital, which contains this unpaired electron, right? This unhybridized p orbital contains unpaired electron, right? So when a reagent like this will approach, right, it will accept its electron in this unhybridized p orbital, right? Because one orbital can have 2 electrons, and as of now it has only 1 electron, right? So when a reagent approaches, it will accept the electron in its unhybridized p orbital, right, to form a bond, right? I hope this is clear. Now if we talk about the stability, right, if we talk about the stability of these free radicals, stability of these free radicals is explained based on the hyperconjugation, right? So more is in hyperconjugation, if you remember, more are the number of hyperconjugative structures, right? More are the number of CH bonds, right? So more hyperconjugative structures. More hyperconjugative structures means more reactivity. More stability, right? So here you have maximum CH3 bonds, right? You have maximum CH bonds in tertiary free radicals. So tertiary free radicals have maximum stability, right? So these have maximum stability based on hyperconjugation, right? Because it depends on the resonating structures due to hyperconjugation, right? So this has maximum stability. After this comes this, because it has two CH3 bonds, right? So this structure, secondary radical, have less CH bonds compared to tertiary, right? And minimum number of CH bonds are with the primary one, right? When we talk about CH bonds of group that is connected to the carbon atom, right? This carbon atom. Here you have only one in case, right? So here you have minimum number of CH bonds. So minimum hyperconjugative resonating structures, right? So less stability, right? So if you go by stability, it would be like this: CH3, CH3, CH3 greater than CH3, CH3. This is your H, right? And you have minimum stability with this, right? And minimum stability is of free radical if it doesn't have any alkyl group attached, right? Because we will be looking into the CH bond of this group, right? And you can see this tertiary 3-degree radical have maximum number of CH3 bonds, right? 9, and in this case you have 6, right? So this is the cause of its stability, right? And its its high reactivity is due to its unpaired electron in this unhybridized p orbital, right? This unpaired electron in unhybridized p orbital will immediately accept an electron from a reagent in an organic reaction to pair up its unpaired electron, right? Now let's quickly move on to heterolytic bond fission. In heterolytic bond fission, like I said, we get a carbocation and a carboanion, right? So in this carbocation, what you get is like this, right? Same as this, carbocations are also primary, secondary and tertiary, right? Based on the type of carbon atom. If the carbon atom is primary, you have a primary carbocation, and in primary carbocation, that means it's connected to only one carbon atom or no carbon atom, right? Then you have a secondary carbon atom, right? Then you have a secondary carbon atom, carbocation, which is connected to two other carbon atoms. Then you have tertiary carbon atom, which is connected to 3 other carbon atoms, right? And it has a positive charge, right? So this is your primary or 1 degree, secondary or 2 degree, 3 degree, right? And just look at this, how many electrons does a carbocation have? It has 6 electrons. If you see, 2 electrons of this bond, 2 from this bond, 2 of this bond, 6 electrons, right? And where are the 2 electrons? When a heterolytic bond fission has taken place, the 2 electrons are taken up by the heteroatom that has a high electronegativity, right? So now it is left with only 6 electrons. So it has 6 electrons, right, which we also call is a sextet of electrons. It has only 6 electrons. So this is highly reactive because it will try to complete 8 electrons in its outermost shell, right, by accepting 2 electrons, right? And if we talk about its stability, we'll explain its stability based on inductive effect, right? And as per inductive effect, we look at inductive effect, we know that if you talk about tertiary carbon atom, it is connected to say 3 methyl groups, right? And we know that methyl groups are electron donating, right? And this carbon atom has a positive charge. So electron donating means it will disperse or neutralize the positive charge on this carbon atom, right? And the reactivity of this tertiary butyl is due to the positive charge. So when you have more number of methyl groups which are electron releasing, they will try to disperse this positive charge on the carbon atom, right, and making it more stable. Similarly, if you come here, this one will have less stability compared to this. Why? Because it has only 2 carbon atoms connected, say 2 methyl groups, right? So dispersal of positive charge is less compared to tertiary. Similarly here, it has 1 carbon atom, 1 methyl group or no methyl group, right? So dispersal of positive charge is minimum here, right? So this has maximum stability, this has minimum stability, right? So if you talk about stability, stability would be 3 degree has maximum stability, then 2 degree, then 1 degree. If we talk about reactivity, reactivity is reverse of stability. If it is more stable, it is less reactive, right? So this is more stable, so this is more stable, this is least reactive. This is least stable, this is more reactive, right? So this is more maximum reactivity is of 1 degree, then comes your 2 degree, then comes your 3 degree. So reactivity of tertiary is minimum because it has maximum stability due to plus I effect of methyl groups, right? All 3 methyl groups would be able to disperse the positive charge on the carbocation to the maximum extent, right? So this has minimum reactivity and maximum stability, right? Now let's quickly look into the structure. Carbon atom is again sp2 hybridized in case of this carbocations, right? And it's like this. You have, it is sp2 hybridized, so it will again have 3 bonds, 3 sp2 hybrid orbitals, right, like this. Right, suppose let's take this or take case of any of these, right? You have a positive charge here and you have 1 p orbital which is unhybridized. This is your unhybridized p orbital, right, which is empty, right? Here the 2 electrons are taken up by a highly electronegative atom, right? So this is your empty p orbital, empty p orbital, right? And its reactivity is due to this empty p orbital because when a reagent will approach, it will accept the electrons in this unhybridized p orbital. I'm sorry, unhybridized empty p orbital, right? So here you have sigma bond, sigma bond, sigma bond and 1 empty unhybridized p orbital, right? And this is your, you have this carbon atom is sp2 hybridized, so its structure would be pyramidal or planar, right? So the other which is left is your carboanion. We'll take this in next lecture, but let's just do it. Same as carbocations, carboanions, in carboanions, your carbon atom is negatively charged, right? And it has a pair of electron, right? From where that pair of electron came? From the heterolytic bond fission, right? When the heteroatom has less electronegativity and carbon has more electronegativity. So when carbon has more electronegativity, it will pull the electron pair towards itself, right? So it has a pair of electron that is responsible for its high reactivity. It's like this. So if you look at its reactivity, if it is like this primary, sorry, this is tertiary and this is your primary carbocation, carbanion, I'm sorry, and this is your secondary 3 degree, this is your 2 degree and this is your 1 degree which is connected to 1 or no carbanion, right? So if you try to understand its stability based on inductive effect, this is a negative charge, so more methyl groups will increase the negative charge on this carbon atom, right? That will decrease its stability, right? and here when you have minimum where you have minimum